Surface tension is also involved in another process. Surface tension is what's responsible for the formation of a meniscus, right? You've all seen a meniscus form, say in a burette, that you have water and a glass interface. Glass has SiOH, silanol units on its surface, therefore it is a polar surface. It's a hydrophilic substrate. Water gets attracted to it and runs up the glass interface here. If, on the other hand, you'd take glass and put it in mercury, you would have a hydrophobic interaction. Or if you had oil here and glass, right? Or if you coated the outside of the glass with, say, hydrocarbons, right? Then if you had water, you'd have a less attractive interaction than on a hydrophilic substrate. And the meniscus actually goes the other way. It looks like a depression rather than a rise. Capillary rise and depression, they're a consequence of that pressure difference across the curved interface. And we already saw that the radius of curvature, right, changes the force balance. And that's what leads to the capillary effect, right? And that radius of curvature, we'll call that the capillary radius. And it's going to lead again to a pressure imbalance. There are going to be forces that are pushing water up, but then gravity is going to try to pull it back down. When those two forces balance, the height of the column will reach its equilibrium value. And that equilibrium value is related to the curvature of the interface, the density of the liquid, its surface tension, and this contact angle. The contact angle is defined here for these two cases. When a system is completely wetting, then the contact angle goes to zero. Right? If we were to put a drop on top of an interface below it, it would spread out and just you'd have a contact angle of zero. Whereas if the drop remains spherical when it is placed on top of the substrate, then your contact angle would be 180 degrees and you'd have a super hydrophobic interaction. Now you may recall that when we were talking about the supercritical phase, we saw this behavior. As we approach the supercritical phase, both of those go asymptotically to zero at the critical point, right? Because you can't tell the difference between a liquid and a gas in a supercritical fluid, right? And so at that point there's no distinction between those two phases. And instead we call that a supercritical fluid. How might this be related to some interesting effects with capillarity? Well, a little bit roundabout, but watch this. Let's say we made a porous silicon film, and then once we had made that by etching, we need to rinse out the etchant, and that rinsing is done with an aqueous solution. In this case, I made a porous silicon film with about 4 nanometer pores. When water enters those pores and starts to evaporate, a meniscus is going to form within the pores. Those small pores lead to large forces acting on the pore walls, and it can destroy the porous film when you have such nanoscale type forces. So capillary forces can tear apart nanoscale objects during drying. Is there a way to avoid that? And the answer is yes, because not only do delta S and delta H go asymptotically to zero at the critical point, also the surface tension does. And so we can greatly reduce or eliminate capillary forces if we can use a supercritical fluid for drying. So how might we be able to do that? The strategy is the following. If we had pores that were filled with water, then, or some other fluid, then we increase the pressure before increasing the temperature. Eventually we could reach the supercritical fluid where the surface tension goes to zero. Now we bring back the pressure to atmospheric pressure, and we can cool back down to room temperature, and we could do so without ever going across the liquid, the vaporization boundary, right? The liquid to gas. If we can go through the supercritical phase along this path, then we can avoid capillary forces and stop this type of damage from occurring. If you've ever wondered how people get SEM images of flies and things like this, they have to take advantage of this supercritical drying technique in order to do that, so that very small objects like the hairs on a flea's head don't get damaged by drying effects.